Good morning, everybody. All right, so this morning we're going to be looking at James Lovelock and the Gaia hypothesis. And I think that's a nice little program. It's about an hour and 10 minutes long on the video. And then we'll have a little discussion afterward. But let's start by moving our chi a little bit. Okay, put away your sticks. So Jose, are you there? Jose, if you're there, come online. There he is. Okay, so I wanted to ask you guys, we're going to be watching a couple of videos that focus on James Lovelock and the Gaia hypothesis. How many people have ever heard of this? Okay, all right. How many people know a lot about it? A little bit. Well, you're going to know a lot more before this is all over. I actually had to divide this up into 2 weeks. So we're going to watch volume 1 this week and we're going to watch volume 2 next week. This first volume is going to focus really more on, a little bit more on Lovelock as a human being and kind of a very general picture of this. And then next week we're going to go more into the nuts and bolts about how this actually works. So let me go ahead and play this, put this on. It's like an hour and 7 minutes long, something like that. It'll probably end up being like an hour and 15 minutes because I'm going to stop at point to point and make a few comments. And then we'll just have a very general discussion afterwards. All right, so make yourselves comfortable. Let me cue this up. Yeah, good idea. By the way, I should say, this is fairly rough. I have not had a chance to go in and edit everything correctly. So what you're looking at again is kind of a rough draft, and we'll build on that as time goes on. Annie went to get herself a lap robe here. She's a little cold. Okay, let me cue this up and we'll watch it. So I want to start by telling you a story. Once upon a time, a very okay.
That it? Okay.
That's as loud as it'll go.
All right.
Long time ago, when people still believed the world was flat, there was a young person who thought about all this and wondered, what does this flat earth rest upon? I could see the stars above, but what is below? Well, they couldn't figure this out, so they went to one of the old wise elders of the tribe and asked them, what does the world rest upon? And the wise elder said, well, the world rests upon the back of a giant turtle. And the young person thought about this for a while, and then he asked the elder, well, what does the turtle rest upon? And the elder replied, well, it rests upon the back of an even larger turtle. And the young person thought about that for a while, and then he asked, well, what does that turtle rest upon? And the elder replied, look, it's turtles all the way down. Now, that's a funny story, but it's also a really profound story because what the young person was asking is, what does the world rest upon? What stabilizes the world?
That turtle's in love with that cat.
So for me, the transitional idea from being a mainstream scientific ecologist to being a more holistic kind of scientist was Gaia theory, the idea that the Earth is one vast self-regulating being, that the Earth is alive, that it has a physiology, just like we have a physiology, and that this livingness of the Earth comes about because all the living beings, plants, animals, bacteria, fungi, etc., interact intimately with the so-called non-living aspects of the Earth, the rocks, atmosphere and water. And when they interact, something emerges from that interaction which you couldn't have predicted from a knowledge of each of the parts in isolation. And that is that the whole is able to regulate its surface conditions within the limits that life can tolerate over vast spans of geological time. I mean, that for me was an idea that was, of course, highly scientific, but it also opened up for me a whole realm of feeling, a whole realm of intuition, a whole realm of sensing, which I was really looking for all my life.
We're not Newton's machines. We're part of an incredible series of living systems that spans the Earth. I visited James Lovelock in the west of England. He's a chemist whose work has been a revelation to me. Almost 40 years ago, he perceived the largest living system of them all, the one that's kept the planet fit for life since life began.
To begin the story, I was a science fiction addict. I had been since a kid. I really loved it. And when they started exploring space, it seemed to me, you know, almost a dream come true. And I'll never forget the day I had a letter from the Director of Spaceflight Operations of NASA inviting me to join in with their first moon landing expeditions, to be one of the scientists responsible for analysing the surface. You know, to me it was just like a love letter. It was one of those really exciting events of a lifetime.
While he was with NASA, he joined a group of scientists searching for signs of life in the solar system. He wondered how we could detect life on another planet without going there. He focused on the planetary atmospheres. What he found changed the way we see our world.
When you look at the atmospheres of our three planets, Earth, Mars and Venus, they are enormously different. Mars and Venus, which are dead, both have atmospheres which are dominated by the gas carbon dioxide, which is what you'd expect from the distribution of elements. But when you look at the Earth, it's a totally different matter. We have methane, hydrocarbon and oxygen, and they're reacting all the time, burning like a cold flame in our atmosphere. If you were a Martian astronomer, so to speak, looking at the Earth to detect signs of life by atmospheric analysis, it would shout back at you, we're a living planet and there's no question about it. All sorts of things would come back immediately from the atmospheric composition. And it began to come into my mind at that moment, and I remember it very vividly. Well, if our atmosphere is so extraordinarily different, so reactive, and yet it stays constant for millions of years, something must be regulating it. And since I knew that these gases all came from living organisms, it must be life that's doing the regulating. So now I had my idea of a system on the Earth that could regulate the climate and the chemistry.
That all came together in that just, wow, what an exciting moment.
It was an exciting moment.
James Lovelock saw the planet as a living entity. He saw how the totality of life on Earth creates and maintains the conditions for life, cycling the crucial elements: earth, air, fire, and water. It was a new vision for science, but one with deep roots in human tradition. He named this planetary entity Gaia, after the Greek goddess who first drew the world from chaos, breathing life and form into matter.
The practice of science has shaped the modern era. But how are discoveries made? And how does science progress? 3 British scientists, world leaders in their fields, have changed our understanding of our universe, our planet, and ourselves. A physicist whose mysterious radio signals from space rewrote astronomy.
She actually recognized that there was something happening. I suspect that perhaps only 1 in 100 people would have spotted it.
A chemist whose radical theory about our planet divides the scientific world.
He's one of the greatest thinkers of the current age, and destined to go down in history.
And a biologist who discovered the secret of life in a sea urchin.
Your fundamental discoveries have profoundly increased our understanding of how the cell cycle is controlled.
Their stories tell us about the nature of scientific inquiry in the modern world, about how scientific breakthroughs are made, and about the workings of the scientific brain.
I never dreamt, you see, when I started out doing science, that I'd be involved in a highly controversial theory. You don't think that at all. My initial ambition always was to work in the lab and do hands-on science, just like an artist wants to be with his brushes and paints and canvas and things will come along. He doesn't expect to produce a masterpiece, does he?
GAIA, G-A-I-A.
This is a man who thinks the world is coming to an end.
James Lovelock is responsible for the Gaia theory.
Planet Earth is a self-regulating system,
which seeks to explain why the Earth behaves as it does, was a landmark in modern science.
It's going to play absolute mayhem with our civilization in the next 10 or 100 years.
He may be right, and he's had a track record of being right in the past, so he may be right in this case too. I hope he isn't.
Stunned the world and divided
the scientific community. It proposed that the Earth is...
I wanted to make a comment on what that guy just said. Sorry, I was so busy watching this, I skipped over it.
Planet Earth is a self-regulating system,
which seeks to explain why the Earth behaves as it does, was a landmark in modern science.
It's going to play absolute mayhem with our civilization in the next 10 or 100 years.
He may be right, and he's had a track record of being right in the past, so he may be right in this case too. I hope he isn't.
I wanted to comment on, I hope he isn't. It's true that the kind of thing that Lovelock is forecasting is very difficult. On the other hand, nature is ruthless. And if it requires something difficult to come back into balance so that we have a long-term ability to keep existing, it may be necessary. So I'm very cool to the point of cold about saying something is either good or bad. What I'm interested in is just seeing what's actually happening.
James Lovelock's scientific masterpiece, his Gaia hypothesis, stunned the world and divided the scientific community. It proposed that the Earth is able to regulate its own atmosphere, and that to interfere with that process would lead to catastrophe.
It is important, it's extraordinary, it's incredibly timely. It can be compared with the revelations that we're not at the centre of the universe.
I would rank the Gaia theory as being in the same category of scientific advance as Darwin's theory of natural selection.
For many, Gaia theory was a milestone in our understanding of the planet. A way of looking at the world so different that it challenged not only scientific orthodoxy, but also the way in which science is practiced. A challenge launched not from a school of thought or institution, but from one extraordinary individual.
I think James has two related qualities which go some way towards explaining his evolution as one of the most important scientific thinkers of the last century. And the two qualities are individualism and directness of mind.
Lovelock can think in straight lines, but he can also think round corners.
James's capacity to think outside the box is exactly because he doesn't recognize the box.
For some, James Lovelock is a maverick. Certainly he is an outsider. Lovelock himself insists that minds like his can only work outside the confines of the mainstream scientific establishment. And so for 40 highly successful years, he's been pursuing science on his own, having abandoned the labs of NASA and British academia for his garden shed.
Snuggled deep in rural Wiltshire is a thatched 16th century cottage belonging to Professor James Lovelock. Today, the lone wolf scientist is considered a somewhat freakish rarity. And indeed, for more than 20 years, Professor Lovelock conformed, working in large research institutes here and in the USA. But a couple of years ago, he kicked over the traces and became independent.
If you work in a large institution or a university, it's quite difficult to do more than about 20 minutes work a day, what with interruptions and telephone calls and so on. And for another thing, I think scientists are a bit like artists, and who in their right mind would think of cooping up a bunch of creative artists in an institute or a university? It was the way of life I wanted to follow, was being an independent spirit working on my own. Perhaps I'm much more greedy than the others. I want the whole damn show. I just want to be a scientist. Totally blue sky, not done for money, done for curiosity and interest.
Lovelock believes it's his unfettered approach that's led to a string of remarkable scientific inventions and discoveries.
Oh, we're just off to look in the lab. If you can call it a lab. It's where I do my, keep my toys and do experiments. Don't be frightened of the notices on the door. They're more to pacify health and safety than representing any serious dangers. I've made nearly all the instruments I use. If you build something and make it yourself, you have an automatic understanding of how it works and what it is that you would never get by mere reading about it. If your hands are not involved in your scientific work as well as your brain, it's not as good.
I remember that when I went into his house, it was like as if he lived slightly at an angle to the rest of the world. He didn't see things in the same way as anybody else that I'd met. It was very disorientating. It made me feel slightly giddy, actually. Yeah.
There's an accumulation of 33 years of bits and pieces. You wouldn't see much of this sort of equipment in any modern lab anywhere nowadays. Here is an electron capture detector. This invention was come upon serendipitously. That's to say, as a sideline, I set out to find one thing and found something better. And this is the secret of all good inventions. Some have said the electron capture detector did more than anything to start the green movement going. I won't go into the full details of the reaction, but the point of this thing is it's more sensitive than any other simple chemical analytical detector that's ever been invented.
This device is quite exceptionally sensitive, more so even than an animal's nose. And that's quite remarkable, for it's not often that one can do better than nature.
Lovelock's invention thrust him into the public arena because it showed disturbing evidence of man's impact on what an embryonic green movement was starting to call the environment.
The pesticide problem is an application in which this invention proved its worth. We're now alerted to the dangers of an uncontrolled use of pesticides and the build-up of man-made chemicals in the tissues of animals and man. Traces of DDT have even been found in the fat of penguins, and it took Professor Lovelock's electron absorption detector to spot the minute quantities involved.
His electron capture detector, that's really what made him famous. You know, that in itself would have been an extraordinary career for one person, you know, proud and destined to go down in history. But Jim's done so many other things as well.
My earliest encounter, quite definitely, with science was in Christmas. I think I'd forgotten which year, it was 23 or 24. My father, as a present, gave me a box full of tricks, as he called it. And all there was in the box was lots of wires and batteries and bells and lights and buzzers and things. He said, there, join that up and you'll have some fun with it. And I was fascinated with it. Spent a lot of time finding out how the things worked. And it was the best Christmas present I think I've ever had. And then I got puzzled. I couldn't understand why it was you need two wires to send electricity along, whereas if it was gas or water or something, you just need a single pipe. And I started asking around, first my father and then my grandmother. Nobody knew, not even the postman. And so I realized I'd have to do it myself, find out. And that's what I think set me on a life as a scientist.
James Lovelock's father not only set him on the road to becoming a scientist, he also unwittingly paved the way for his next, and perhaps one of his most important discoveries: the build-up of CFC gases in the atmosphere.
I think I learnt my ecology, if you like, from my father, because we used to go for walks at the weekend. He would take me through the countryside and show me all the tracks of animals. It was a feeling for and an understanding of the countryside which has remained with me ever since. What's the connection between country walks and looking for CFCs? You see, the story goes like this. I remember from my walks on Leith Hill with my father how often one could see the Sussex Downs. The air was always, in those days, quite clear. Now, very strangely, many years later, one of the things that struck me immediately was how different it was, in that very often during the summertime there was a dense haze. Where on earth does it come from? That was the question I asked. At first there didn't seem to be any answer, and then it began slowly to dawn on me. It probably came from the nearest highly populated area. And I could prove that if it was sort of human haze and not some kind of natural phenomenon that had happened since I was young, by analysing the atmosphere to see if it had some unequivocally human industrial compound in it. And I thought a bit, and the obvious and only one to choose were the fluorocarbons, the CFCs, because with their spray cans and leaking refrigerators, the only thing on Earth that releases CFCs into the atmosphere is people. It's a people marker. So all I had to do was to see if the presence of haze correlated with the presence of an increase in the amount of CFCs.
I suppose it was very unusual. I mean, most scientists have a laboratory with lots of staff. He had my mother, my Auntie Betty, myself, my brothers and sisters. You know, we'd all be helping.
They were only too happy to join the routine of daily measurements, and Christine did an awful lot of the haze measurements.
We were just helping as if, I suppose, you might help on a farm or something.
Sure enough, it showed a marked correlation between the haze and the presence of CFCs. At that time, I didn't realise I was the only person in the world that was measuring the CFCs. Nobody took the slightest notice. They weren't in the least interested either in the presence of CFCs in the atmosphere or in haze. But the puzzling thing I found was that there were still CFCs in the air even when the air was sparklingly clear. And I thought then, is it building up in the whole atmosphere of the world without any kind of losses? And I was curious about this.
The lone scientist, working from home with part-time assistance from his family, was on the verge of making perhaps the most significant scientific discovery of the 20th century.
His mind is able to make intuitive leaps or connections between things that the rest of us would always keep separate in our heads. And it's those connections that he's been able to see that have been the most remarkable scientific advances that he's gifted us.
It suddenly dawned on me, oh, what a marvellous excuse to go on a ship voyage from right the way down to Antarctica to find out were the CFCs in the whole world atmosphere or not. You followed your nose. And that what makes your science real. That's what makes you want to go on doing it. And it had a wonderful captain. We'd often have good discussions in the ship's dining room after dinner at night. He'd taken the precaution to bring along some very good wine. It was a very pleasant atmosphere. And all I had to do was to go out several times a day with a hypodermic syringe and fill it with air, and then take it back to the lab and inject it into the gas chromatograph. Quite remarkably, I found that the fluorocarbons were in the atmosphere of the whole planet. So they were just adding up in the atmosphere without going anywhere. I did what scientists usually do. I wrote it up in the form of a paper, which was published in Nature. I didn't realize I was letting loose the CFC ozone business and shutting down a billion-dollar industry in the course of it. You see, the scientists in California, Mario Molina and Sherry Rowland, developed the idea that the CFCs going into the stratosphere would be a source of chlorine, and this would destroy a significant amount of the ozone layer. And of course that hit the fan in a big way.
Within the past hour, more than 90 countries have agreed on a plan to try to save the Earth's ozone layer. The meeting has been taking place in London. The agreement commits the countries to phase out chlorofluorocarbons, or CFCs, within 10 years.
It was the connection between the build-up of CFCs and the hole in the ozone layer that shifted the environmental movement center stage and earned a Nobel Prize for Molina and Rowland.
He deserved and didn't get a part in a Nobel Prize, but then, well, the fitting tribute will be if somehow his ideas actually help us find a long-term sustainable future on the planet. That's worth a lot more than the recognition of the establishment.
I grew curious about the nature of things and fell in love with science at least 80, probably 82 years ago. My mother was an avid reader, and she always went to the Brixton Library, because those days people didn't buy books, certainly unless they were very rich, and you went to the public libraries, and they were everywhere. The Brixton one was exceedingly good, and she would go and get her political books on feminism, because that was the kind of thing that turned her on, or on socialism. It didn't matter, one or the other. And I went at first to get science fiction, and came back with H.G. Wells's wonderful books. I think that they really filled in my mind a lot. I mean, the story of the time machine, I mean, it was so different. I mean, that was the start of real science fiction. But that wasn't enough for me. After a while, I wanted the hard stuff. And they kept the hard stuff in the basement. And that was really a cornucopia, a cave of wonders. The kind of stuff you pick up when the mind is developing before puberty stays there for good. And you do feel intensely when you're a kid of that age. Everything is full of, life's full of feeling. I was mining magic down at the basement of Brixton Library. And I went on doing it all the time, and it solidified. I really had struck a few mother loads down there. I don't think I understood much of them, but your mind is a kind of sponge. And it stays there in your machine language memory for the rest of your life. So that from then onwards, my mind had a complete understanding of the position of all the chemicals and their properties and things, although I didn't even know what the properties were. But later on, when I came to be a professional chemist, then all of that knowledge was there instantly accessible whenever I needed it. Why did I choose chemistry as my subject in science? After all, if you go back to that box of tricks my father gave me, bits of wire and stuff, that's physics, that's not chemistry. Why didn't I go into physics? It so happens that I'm dyslexic, and not seriously. I can't tell the difference between left and right is one of the peculiarities. It also meant that in mathematics, I can never tell which side of an equation I'm on. And in finding the answer, the solution, this is quite a handicap, You get there in the end by just testing, trying both ways and seeing which one is right. But this wastes an awful lot of time, and when it comes to examinations, if you're slow, you don't pass. I was fascinated by physics and maths, much more than chemistry, but I realized practically that because of the slowness in handling mathematics, I couldn't satisfy the examiners on physical things. The best way of thinking of it was that I'd fallen in love with science at some age, and I just wanted it around me as you want a loved one around, nearby and always available.
Though he had studied chemistry, Lovelock always saw science as a single entity. And when war came, the fledgling polymath was unexpectedly exposed to an even greater array of scientific disciplines.
Out of the blue came a letter from the National Institute for Medical Research saying, would I be interested in a job with them? And the first thing that Sir Henry Dale said to me, he said, my boy, he said, don't expect to do any science when you come here. He said, we're at war now, and it's going to be nothing but wartime problems, ad hoc problems, that need an answer yesterday, preferably. One of the duties of everyone working at the National Institute for Medical Research, that included everyone, quite literally, was to fire watch, to patrol on the roof of the Institute one night a week. Now, in the course of this, I met all of the senior scientists in the Institute, and it was quite fascinating, because when an incident occurred, like a V-1 missile coming close by, on one occasion it was coming on a course which looked as if it was coming towards us. Came so close by that we could see the rivets. We began to get a little bit excited, to say the least, and then it cut out. In their fear, the senior scientist that I happened to be with would open his mind and do a brain dump and see me as the young person near him. He got to pass on all the accumulated wisdom of a lifetime, and you learnt more in those little incidents than you ever would, and many of them would never normally speak to you. They were sort of senior old buffers that guarded their privacy an awful lot. Boy, did they open up when the bombs came near. I learned from these encounters an amazingly widespread vision of all the branches of science that were included in that institute. Physics, chemistry, bacteriology, virology, you name it, all of them. And it all helped to build up in my mind the broad picture of science as one single subject.
I've worked with him on and off for some years now, and I think the lasting impression that I'll carry with me forever is his encyclopedic knowledge of maths, physics and chemistry and biology and medicine, and his personal experience that he draws on in everything he thinks about and does.
Nowadays, science specializes and specializes. You can get very good about the microorganisms that attack a certain form of bacterium and their genome and all the rest of it, but it doesn't take you very far about understanding the world.
It's this holistic way of thinking and lack of adherence to a single scientific discipline that marks out Lovelock's unique approach to science, an approach that he believes was fundamental in developing Gaia theory.
You see, nearly all scientists nowadays are slaves. They're not free men or women. They have to work in institutes or universities or government places or industry. And they have to work on a specific problem. The very few of them are free to think and outside the box, so to speak. So you come along with a theory like Gaia, and it's so far beyond their normal experience, they're not going to be able to react to it.
3, 2, 1, 0. shot of Earth, live on television.
The thing that kicked Gaia off, mainly, was, of course, NASA. There would have been no opportunity before that for people to have considered the Earth from outside in reality. One day, a letter arrived on my desk that was from Director of Spaceflight Operations for NASA, and it was an invitation. Would I like to be an experimenter to look for life on Mars?
If there is life on Mars, then there will be a simply fabulous expansion of the perspective of the biologist. Because all the organisms on the Earth, even though they seem to be different, are fundamentally the same. Their chemistry is all identical.
I went along to this meeting of biologists about various experiments to detect life on Mars that NASA's going to send there on one of the future missions.
The first thing we'll have to do is organize a team, the best we can get.
Most of the experiments that the biologists were doing were based on the assumption that life on Mars would be very like life in the Mojave Desert. If their experiment could detect life in that desert, then it could probably detect it on Mars. One very keen biologist took me by the arm and said, "Let me show you my life detection. It's an absolutely experiment for Mars. It's bound to work. It can't possibly fail." And what he showed me was a little stainless steel cage, about 1 cubic centimetre in size, and it looked very beautiful. And I said, "What's that?" And he said, "It's my Martian flea trap." And I said, "Why do you think there's fleas on Mars?" He said, "Well, everybody knows Mars is nothing but desert. And where you get an extensive desert, you always have camels. And there's no animals with more fleas than a camel. This will detect life on Mars."
Is there life on Mars?
So I started being stroppy and saying, "Well, how the hell do you know that life on Mars is like life in Mojave Desert? It might be totally different. It's a different planet altogether. Might not even have the same form as life on Earth." And this made them very cross. And they thought that I was bullshitting, really. Is that a technical term? Anyway, they complained to the director about it. He was a tough guy, and so he said, "Well, what would you do?" And I said, "Well, I've got to think about that." He said, "Well, you have until Friday." And I knew that my contract was kind of on the line. I got until Friday to come up with an answer. And that's the kind of thing that really stimulates thinking. I was scared.
Jim is at his best when he's posed a problem, I think. Give him a puzzle and he's brilliant at solving them. And what's brilliant about his thinking is that he thinks out of the box. He doesn't imagine what we might put on the landing craft and how it might measure the soil. He says, although there must be a much more general way of recognizing life.
Suddenly came to me. Finding life on Mars is the simplest thing in the world to do. All you had to do was measure the composition of the atmosphere of Mars chemically. That was all. Just find out what gases were in its atmosphere.
He had the realization that if life was abundant on a planet, it would change the atmosphere of that planet. And then he could take that a step further and realize that you could tell whether there was life on Mars or not without having to go there.
You can do it with a regular telescope, but using an ultra-sensitive infrared analyzer.
Lovelock felt that if the Martian atmosphere was inert and unchanging, there could be no life.
My argument was, if there was life on the surface, then it would be obliged to use the atmosphere as the source of materials to make itself. And it would also have to use the atmosphere as a place to deposit its waste products. And doing that would change the composition of the atmosphere in a way that would reflect the existence of life.
For there to be any chance of life on Mars, there would need to be a variety of gases present in its atmosphere. Lovelock and NASA held their breaths.
In September 1965, I met in a room with Carl Sagan And in comes another astronomer, Lou Kaplan, carrying sheets and sheets of paper. And we said, "What's this?" He said, "It's the complete analysis of the Martian atmosphere." What this analysis showed was that Mars had atmospheres that were almost nothing but carbon dioxide, just bare traces of other gases present. And I knew immediately this meant Mars was probably lifeless. At that moment, suddenly a thought came into my mind, but why is the Earth's atmosphere so amazingly different?
It was this realization, and the logic that provided it, that prompted Lovelock to think about our own planet in a radically different way.
The Earth was a remarkable planet. How does it stay always habitable? All the billions of years. We've got oxygen mixed with methane that would be explosive if it were different in composition. And then it occurred to me that both gases were made by living organisms at the Earth's surface. If they were making them, maybe they were regulating them. It was a eureka moment. I sort of blurted this all out, that, oh, the Earth must be a great self-regulating system, almost alive, that's holding its atmosphere constant. And this shook the others, particularly Carl. He said, "Oh, you couldn't possibly be right, Jim." And then he thought for a moment. He said, "But there might be something in what you say, because we astronomers have known that one of the great puzzles is that the sun has warmed up 30% since the Earth formed. So if it was warm enough for life to start, why aren't we boiling now?" And then immediately it occurred to me, well, if the organisms can regulate the amount of gas in the atmosphere, then they can regulate the temperature. We know it. We've only put 6% more CO2 in the atmosphere, and we're all in trouble already. It doesn't take much to change the temperature by changing the gases. It was life that looked after the atmosphere and the climate.
His eureka moment. He realized that Earth had this incredibly unusual atmosphere because of the presence of life. And then he could make an intuitive leap to the idea that that might mean that life was somehow involved in self-regulating the state of the atmosphere and the climate. It's those intuitive leaps that must require an unusual mind.
It wasn't until you started asking questions about Mars and thinking about its atmosphere and the effect of life on it, that you suddenly start looking at the bits of the Earth, like the atmosphere and the oceans, in a totally different light.
His single greatest contribution to science has been to say you must look at the Earth top down as a system, looked at from above, forgetting the disciplines of geology, biology, meteorology.
You can't take the top-down view if you're tied into a single discipline. It's only if you've got it all in your own mind, in one go, that all the bits and pieces come together. I was lucky enough to have had strong hands-on experience in chemistry, in physics, making instruments, in biology, working with animals, with bacteria, with all sorts. Science was one open board to me. I wasn't tied into a given discipline, as most of them are.
The first law of thermodynamics. Heat is work, and work is heat.
I've always been mischievous, and I think my school days made me that.
The second law of thermodynamics.
I got frequently caned.
Heat cannot of itself pass from one body to a hotter.
You see, I'm a fairly amenable sort of non-rebellious person, but circumstances drove me that way.
Heat won't pass from a cooler to a hotter. Then try it if you like, but you'd far better not.
You could try it if you like, but you're far better not.
I was very happy to go to a grammar school. At last I was being taught science. Nothing could really dispel the disappointment I felt when I found that the real science was almost unbelievably dull that was taught.
And work is heat, and heat is work.
Heat will pass by, conduction and heat will pass.
And there I went through a dangerous period of almost becoming turned away from it.
And that's a physical law. Heat is work and work's a...
I remember on one occasion we were given a general knowledge examination which was set for the top classes of the school, which included the sixth forms, and I was in the fifth form. And I was lucky enough to win the first prize in this examination, which irritated the establishment beyond belief. It was not what they'd expected would happen at all. I was harangued in front of the school on the grounds that I was not intelligent. I was a freak, just a storehouse of knowledge who had accidentally managed to answer all the questions on the examination. I think demeaning and ill treatment of that kind with many children would be fatal. It would drive them into depression, loss of all self-esteem. I often thought I had low self-esteem, but it wasn't. It was really a feeling that I was at war with the establishment always, and it doesn't hurt to get warned about them, to deal with them at an early age, and use it to fight my battles in life from then on.
Lovelock's radical idea about the Earth certainly went against the scientific consensus of the day. It had emerged from his work at NASA, but it wasn't until he was back in the UK that it was given a name.
It wasn't called Gaia then. It wasn't until about 2 years later when my friend and neighbour William Golding, the celebrated author, suggested that if I was going to have ideas, large ideas like that about the Earth, I'd better have a proper name. And he said, I suggest Gaia, the Greek goddess. We have a statue which is supposed to represent Gaia here. I don't go out and pray before it in the morning before I start work or anything like that. The first paper that named Gaia was entitled Gaia as Seen Through the Atmosphere. One of the most important things about Gaia is its ability to self-regulate, to keep the temperature, for example, constant, to keep the amount of the various gases in the air within certain ranges, so as always to keep the planet habitable. It was life that regulated the planet and looked after the atmosphere and the climate. After I formulated Gaia, the evidence for it began gradually to emerge. To give an example, the production by organisms that live in the ocean of a strange gas called dimethyl sulfide. What happens is, if the ocean surface water gets warm, the algae grow better. It's like the growth of all organisms. It's faster when it's warmer. And as they grow better, they produce more of the gas, dimethyl sulfide, which vents into the atmosphere and ultimately causes a cloud layer to form over the ocean surface. And clouds are white and they reflect sunlight back to space, and so the more the algae grow, the cooler the Earth gets. Why should the algae want to do that? Well, the reason is they have a need to keep the ocean surface waters cool, because once the ocean surface water rises above about at 14 degrees Celsius, it stratifies, and then the nutrients that are in the lower water cannot enter that top layer, and so the algae living there die of lack of food, quite simply. So they have a strong vested interest in doing anything that will stop the top layer of water from rising above 14 Celsius. So you've got a nice thermostated mechanism there, and the whole thing's beautifully stable. So there was one of the great natural cycles at last explained properly. And it was a small triumph of Gaia, which didn't really hit the fan to any extent. Nobody was interested. So it left me with no option but to write a book. If Gaia does exist, then we may find ourselves and all other living things to be parts and partners of a vast being who in her entirety has the power to maintain our planet as a fit and comfortable habitat for life. There was a lot missing, but it was the skeleton of the body of theory that was to develop.
We believe in one God, the Father Almighty, maker of heaven and earth, of all that is seen and unseen.
I was astonished, quite astonished, to receive letters and phone calls from religious people. One that I remember particularly was the Bishop of Birmingham, Hugh Montefiore.
It made me think of what theologians call the immanence of God. That is to say, the Holy Spirit of God working within creation, and the way in which the cybernetic controls are set up and make life optimal for human beings to appear in so many different ways, which he describes. That immediately put me in mind of the Holy Spirit working within creation.
Christ has died. Christ is risen. Christ will come again.
I found it very easy to engage with people who are religious if they want to think of Gaia as an example of God's creation, a living thing that God created. I'm not saying I think that, but it's a way for them to think about it. I was even more astonished with the interest that the New Age, which was a world I'd not even encountered at all before that.
We don't recognise that we are so intimately connected with the Earth, and that she is so much a part of us, and we are so much a part of her, that if we don't communicate with her and recognise how we can't live without her, we'll destroy the Earth. We'll destroy her and we'll destroy.
My battle with the scientists. They say, you know, look, there's nothing but New Age nonsense.
The initial response to the Gaia hypothesis, as it then was 30 years ago, was extremely hostile, more than negative, often dismissive, scornful, and persisting in developing this theory meant a degree of isolation from the existing scientific communities that Jim was ready to accept.
For the scientific establishment, Gaia was a mystical vision of organisms acting cooperatively to benefit Mother Earth, fanciful nonsense, which, it was claimed, flew in the face of evolutionary theory.
The first serious criticism from the scientific community was an article by the biologist W. Ford Doolittle entitled, "Is Nature Really Motherly?" in which he took Gaia to the cleaners, or rather the theory.
Doolittle said, well, you'd have to imagine a committee of all of the organisms on the planet getting together every year and deciding what the level of oxygen would be in the atmosphere that year, you know, and obviously that's not going to work.
And they employed really talented writers like Richard Dawkins, and I think at the time Dawkins hated Gaia as much as he hates God, if you like to make a comparison.
The danger, it's not exactly distressing or disturbing except to an academic biologist who values the truth. The danger is that they will say things like, the function of oxygen is to do so and so, the function of ammonia is, the function of methane is, because it implies that individual organisms that are manufacturing that gas are doing it for the good of the biosphere.
The main thing that Richard Dawkins said was there was no way for living organisms to regulate anything beyond their bodies, what he called their phenotypes. Regulating the planet, the idea of organisms regulating the planet was quite absurd.
The really key objection was, how could Gaia evolve to be self-regulating? You would need that the organisms on the Earth had foresight in some way.
What they saw as altruism on a global scale. They could be altruistic towards themselves or their kin, but that was the limit. Looking after the whole planet and everything on it was just ridiculous. And this is what stuck in the throats of most scientists. They felt that there was no way for Gaia to evolve by natural selection. It frightened all the other scientists off. Almost everybody else became then anti-Gaian. It became impossible to publish a paper with, on the subject of Gaia in any scientific journal. It was a quite wicked censorship of an idea.
This was all the more frustrating because, as far as I was concerned, Gaia isn't against natural selection. In fact, natural selection is a critical part of Gaia.
I spent a miserable year trying to find an answer to Richard Dawkins' criticisms.
In an attempt to silence his critics, Lovelock set about building a computer model of a planet he called Daisy World. A model he hoped would prove Gaia's validity once and for all.
I mean, it was a model of a simple planet that's orbiting a star like the Sun. And this particular star, like our own Sun, warms up as it grows older. And the only life there is on Daisy World are daisies. One dark and one light. You won't get any germination until the surface somewhere has warmed up to about 4 degrees Celsius. Then the first daisy seeds will germinate. The planet was quite cold. And what would happen at first was dark daisies would be favoured. Had been selected, naturally selected. Being dark, they'll absorb more heat than the surface, so they'll warm up first themselves and then their locality, so they'll start spreading. Quite rapidly, dark daisies grow and then spread and spread and spread, and the temperature zooms up, and so do they, in a strong positive feedback, until you reach a point where the planetary temperature is high enough for white daisies to grow. And then they start competing with the black daisies for space. And as the sun's heat gets warmer, so gradually the proportion of white increases.
If it got too warm, then the white daisies, which tend to reflect radiation away, would cool the planet down. And the system would fall into a regulatory pattern.
And the competition kept the temperature exactly at the optimum for daisy growth. And the whole thing's beautifully stable. Daisy World showed that evolution by natural selection is absolutely vital for Gaia. And there's no foresight. These things all happen by chance. It answered the criticism that life can't regulate the climate of the Earth. Well, they were right. It can't. But when life is part of a complete system, of an atmosphere and a surface and so on, then it can regulate. It's not the life that's regulating, it's the whole system is regulating itself. It applies to the organisms and their environment. And for us on Earth, this means all life takes part in Gaia together with the atmosphere, oceans and surface rocks.
What we find is that the system is locked in a sort of dance in which everything changes together. It's as if everything seems to be correlated with everything else. Just one example, you've got the circulation of the ocean, you've got the amount of ice on the surface as well. All of these things are working, changing in concert. It's almost like a symphony.
Daisy World was enough to allow scientists to start taking Lovelock's theory seriously. And as more and more interdependent systems are discovered, the core ideas behind Gaia are finally moving into the mainstream.
We don't have a model that explains everything, but these things are all linked together and have been the chief stabilizing mechanisms that kept the planet habitable over literally billions of years.
Lovelock's ideas are at the heart of understanding how humanity is now changing those stabilizing mechanisms, and they brought him to a controversially bleak view of our future.
From a Gaian point of view, when we first started interfering with the atmosphere, nothing much happened. It was encompassing it by its ordinary regulating mechanisms. But when it gets too much, Gaia can't cope with it. And this is why I'm afraid, I think, it's going to play absolute mayhem with our civilization in the next 10 or 100 years. And when you see the whole picture, it is really fearsomely bad. I mean, things like the very rapid melting of the floating ice near the North Pole. As the floating ice melts, so less sunlight is reflected back to space by the dazzlingly white ice, and more sunlight's absorbed by the ocean. Just the melting of the floating ice in the Arctic Ocean will add as much heat to the Earth as all of the CO2 we put in the atmosphere to date. And this is why I'm afraid, I think, there's very little we can do about it. All of our efforts to reduce emissions are as nothing. There is no morality about it. If the Earth improves as a result of our presence, then we will flourish. If it doesn't, then we will die off. I fear that not many of us will survive, perhaps. At best, about 1 billion, possibly a lot less than that. Now, how they will die, it'll be by starvation, by war, by disease, who knows? The 4 horsemen really ride when conditions like that happen.
I still think there's a lot to play for, but we will see the face of the world change. We're still in the midst of a kind of scientific revolution about how we, not only how we see or study the Earth, but how we see our relationship as humans with the Earth system or Gaia.
The key lesson of Lovelock's life as a scientist is that he doesn't think in terms of any pre-existing consensus, but he's been able to radically shift the prevailing scientific paradigm to the point at which, from having been almost reviled, it's become part of the way scientists generally now think.
James Lovelock, it gives me enormous pleasure to reward this towering career with the highest honour this society can bestow.
For James Lovelock, now aged 90, acceptance of his ideas is also recognition of the importance of independent and unconventional thinking in science. But whether future generations will be able to...
What he just got there was the Wollaston Medal, which is the highest honor that the Royal Geological Society of the UK offers. He got that 20 years or so ago.
Continue this tradition is perhaps uncertain.
It isn't an easy subject, is it? And people say to me, well, you can say that kind of thing easily because at your age it's not going to affect you anyway. You'll be dead before it all happens. And that's true. Although I'm not so sure that if I live to 100, I think a lot of things may happen before then. But I do have great-grandchildren, and its progeny is the name of the game here.
Man means nothing.
Mind and a dose.
Biochemistry. That's in just a moment.
Hold on.
Chases round this desert. He thinks that's where I'll be. That's why I love me.
I don't know what happened to it. It disappeared.
Well, that was interesting, honey. I hadn't seen that one.
No, I had not seen it either. I just found it this week. So, any thoughts, Kevin?
It reminds me of the Captain Bring Down Chautauqua series.
Genevieve.
The weird time to be a parent when you watch something like that.
That's hard.
Yeah, I think he was feeling the same thing. My own thought, I mean, he has said and written elsewhere that in his opinion, the human race is going to be reduced to less than 500 million people, 300 or 400 million people. So somewhere between 500 million and 1 billion people, providing, of course, we don't blow ourselves up. And I think that that's probably true. However, I think the reduction is going to be less, at least at this point, less dramatic than he was outlining there. So he was talking about as he has in other places, the 4 horsemen of the apocalypse. So war, disease, famine. And unfortunately, that probably will happen to a degree. But something has been happening actually in the last 20 years that has only really become obvious in the last couple of years, except to some professional demographers. And that is global populations around the world are already starting to drop. And they're just dropping naturally. So rather than war or disease or famine coming in, it's simply that the birth rate has dropped so far that the overall population numbers begin to drop. So the UN predicts that the Chinese population, which is around 1.4 billion, is going to drop to less than 700 million by the year 2100. Not by war or disease or famine, but simply because their population, their replacement level is so low now that it's mathematically impossible for them to be anything more than that. The same thing is happening in Russia, and it's happening in most developed countries. It's happening in Germany. It's happening all over the world. Korea, the Korean birth rate is so low that it's so far underneath the replacement level, which is like 2.3 per female, is now something like 0.7 or 0.07. So it's only a third of what it would need to be just to replace their population. So is that good? Is that bad? Like they said in that thing, I think it's really important to look at this without feeling it's a matter of either good or bad. It's just a matter of seeing what's going on. It's like opening your door and looking at the weather. Is it good or bad? Well, it's not anything. It's the weather. You're looking at it in order to understand where you are in reality in this system. The replacement level in the United States is less than replacement. This is one of the things that's firing the right wing up, because the white population in the United States is not replacing itself. It has nothing to do with immigrants or anything. Our birth rate is simply too low. Well, that doesn't have anything to do with anybody else. That's an issue for us to look at. But the truth is, without the immigration, our population is going to start dropping. So it's very interesting. I can, of course, cannot help but apply Tai Chi theory, and by Tai Chi theory, I mean yin and yang theory, not the martial art, but the philosophical way of using Tai Chi as a way to look at the world and understand that it's composed of complementary opposites, which is kind of an early relativity theory. And if you look what's been going on for the past 50,000 years, we've been slowly growing, and then in the past 70 or 80 years, we've exploded population-wise. That was a yang phase. That's a growth phase. Now we're starting to move into a consolidation phase, a contraction phase. That's a yin phase. So it's like saying, well, of course, night is going to follow day. Winter is going to follow summer.
White daisies are going to follow black daisies.
White daisies are going to follow black daisies. And then a little shift around to the other side sooner or later. Anyway, I found it really interesting. I think he is quite an interesting person. They did not tell you, and it's a real complication, why he did not get the Nobel Prize. When Sherwood and Molina got the Nobel Prize for finding the CFCs, considering that it was his work that their work was based on, why did he not receive it? He was actually invited up to Norway. He thought to be interviewed for the Nobel Prize, and I think he was being interviewed for the Nobel Prize. But while he was up there, there was an American ecologist, you may know his name, he's long gone now, named Barry Commoner. And Barry Commoner was a bit of an asshole. And he basically stood up and said, we don't have to pay any attention to what this man says because he is a bought man. Now, what he meant by that was Lovelock earned his living by working for industry. And therefore, he was a bought man. And that's what happened. So they scratched his name off the list. It's pretty nasty that it was part of the censorship that was put on him for many, many years.
Yeah.
One of the only people who really supported him at the beginning and through that period was an American microbiologist named Lynn Margulis.
Lynn.
So Annie and I went to see Lynn Margulis once in one of her speeches.
She was really impactful. When we went to see her, and the first time I ever heard the idea that we were a colony, that
us individually in our bodies,
individually, that we are a colony, and I was like, of course, I just recognized the truth of it, and it shifted my perspective so dramatically and clearly.
Well, she was a very powerful woman, a very powerful speaker, and she was the great supporter of the symbiotic theory. So she supported the theory that mitochondria had actually originally been independent bacteria. Well, it turns out she was right. Yeah. As well as many of the other organelles in the body, not all of them, but or in the cells, but many of them. And so, of course, she was very sympathetic to the Gaia hypothesis, because it's essentially she was looking down where Lovelock was looking up, but they're seeing the same kind of vision. Anyhow, next Saturday we'll look at a couple of other videos that explain the Gaia hypothesis a little bit more and how it actually works. But even today, you can't say Gaia hypothesis with a straight face in the sciences, in the science community. They simply do not allow that kind of anthropomorphization. So what they call it now is Earth System Science. And Earth System Science is basically a holistic, interdisciplinary way of looking at the way things work. And it also includes, and this is something they really soft pedaled in this, and actually in every video I've seen on this, they really don't get into it because it's so complicated. But this has to do with complex system theory and what's something that's called chaotic system theory, which makes it seem like it ought to be chaotic, but in fact it's order out of chaos. And the perfect example was the daisy world that he brought up. The regulation happens because there's a natural way of balancing things. It doesn't require consciousness or foresight. It's simply built into the system itself. And multiply his example by 100,000, and that's the way things work. Which, by the way, is exactly what people thought 10,000 years ago, long before science ever existed. So is the Gaia theory important? Yeah. Is it all brand new? No, it's not. What's brand new is he's put it into language that modern science can see and appreciate and understand. And that's very important. It's even critical. And it does mark a movement up from the kind of intuitive understanding that the idea that the Earth itself was alive is an ancient idea. So it's something that is still very difficult for modern people to grab hold of. The reason I played the material last week before this one was to begin to grab hold of the idea that the biosphere is not something that just happens to be on this dead rock. It literally comes out of the dead rock. It is part of the dead rock. It's not a dead rock.
Not a dead rock.
The earth is alive. And you go, oh, I can't hold that. Let me ask you a question. What is your body made of? Hydrogen, oxygen, nitrogen, traces of everything. So, there's 153 different things. They're all atoms, right? Are any of them alive? Are any of those atoms alive? Then how are you alive? It's the same thing. The earth is literally alive. That's what that's what Eric Smith was trying to tell people last time. They're not two separate things. They're one thing. And what Lovelock is describing is that it all works together to regulate itself physiologically exactly like you do. Keeping your temperature between 96 and 104. How does that happen? You're just composed of things that are not alive. But you are alive. It's not just a kind of interesting analogy, it's a direct analogy. It's not metaphorical, it's literal. Yes, Kevin?
Yeah, this is where that ugly theology raises its head, that we don't reproduce, we don't have a soul, that's not alive if you don't do those things. And it's bullshit, but it's that disconnect between theology and science that still continues in my mind.
Well, organized religion is largely political. It's as badly corrupted as Lovelock was describing so much of science as being corrupted. That in order to think independently, you can't work at a university. You can't work for Shell Oil. You have to be independent so that you can think independently. It's not just the questions you set yourself. It's also the mental paradigm in which you have placed yourself. You have to stay out of the system if you want to see the system.
Yeah, you can't be in the matrix.
Yeah, Kevin.
So I had a 10-year career at Genentech. I don't know, it's now Hoffman LaRoche, but it's still called Genentech. Long story short, all the people working at Genentech were expected to take 10 to 20% of their time working to not work on company projects, to do thinking on their own. And I think that's why that company was so successful, is because you were told to think outside the box and not be caught up in the corporate goals. It mutated over time, when they started making money. But, it still was one of the best places I've ever worked as far as corporation.
Well, it's very unusual to find that kind of awareness and that kind of support in any corporation or government or any situation like that. I don't think that's the general corporate. I don't think Elon Musk is asking people to do that. I think he's asking them to toe the line. But in any case, the point is religion, organized religion, is a part of the matrix. And if you're truly looking for spiritual growth, the best place to look is not in organized religion. So there is still a great chasm between spirituality or call it religion if you want, and science. Most of it based on the history of two different mindsets
Years.
that simply cannot get together. It's a shame because it's going to have to be healed sooner or later, but it may take us up a couple more centuries. Okay, guys, I think we're going to need a couple of minutes here to have a little breakfast before we go into the Tai Chi class.
Oatmeal.
Annie's going to make us some oatmeal. So give me 15 minutes or so, and then we'll start the Tai Chi class. All right, ciao.